So we defined frequency as the number of waves passing through a point per second. For the wavelength in the deep water, we know that the value for or the distance of 4 wavelengths is 6 centimeter, and distance for one wavelength would be 1.5 centimeter. All right, so for 4 wavelengths it was 6 centimeter, for one wavelength it was x centimeter, then with cross multiplication your wavelength would be 1.5 centimeter. Calculate the speed of the wave in the deep water. V equals to frequency times the wavelength, and frequency was given as 5 times the wavelength was 1.5, so the speed would be 7.5 centimeter per second. The wave passes from the deep water into the shallow water. The speed of the wave is less in shallow water. Explain how it affects the wavelength of the wave. Now, as the waves enter the shallow water, their wavelength would decrease. But since the speed also decreases and the frequency remains same, that's why their wavelength has to decrease. So for this one, you can write a statement like this one over here. So I'll just paste it. Wavelength decreases because the frequency remains same. So if the speed decreases, then wavelength has to decrease as well. Alright, then in the next part, the wave in the deep water shown in figure 9.2 travels towards the right and enters the shallow water. So whatever the wavelength here, in the shallow water the wavelength would be lesser. The wavelength would have been reduced. So how do we represent the wavelength? The wavelength is represented by the wavefronts or the spacing between the two consecutive wavefronts. That means on the right side in this portion, the spacing between the wavefronts should be less than this one. If this spacing is 5 centimeter, on the right side the spacing should be less than 5 centimeter. Draw the wavefronts in the shallow water. So if I bend the waves in this direction, you'll realize that the spacing is now increased. If this is 5 centimeter and I bend the waves forward, this one would have been 7 or 6 centimeters. The spacing would be increased. So if you bend the waves backward like this, then this is the only possible way in which the spacing between the waves or between the consecutive wavefronts would decrease. So as the waves enter the shallow water, they'll bend backward. In this situation, they'll bend backward. So what would it look like? The final form should look something like this. Here I have it over here. So this is what it should look like. The red lines and the dotted line, this is the optional stuff. If you want to draw, you can. This one represents that the waves or the wavefronts or the water waves are bending towards the normal. If you want to represent this thing, you can. Otherwise, the green part or the green lines are the compulsory lines which show the refraction of waves as they enter the shallow water. So these green lines you have to draw at least. Moving on to the next one. Sound wave is also a wave. Describe what is the difference between sound wave and water wave. Alright, so that's an easy one. Sound wave is a longitudinal wave, and water wave is a transverse wave. If you want to define longitudinal and transfer as well, you can. Matter of fact, you should. So you can say sound wave travel in the form of crust and trough. In the form of compression and rarefaction, and water waves travel in the form of crust and troughs. The water waves have ups and downs, and the sound waves have the region of high pressure and the region of low pressure. So any of those statements can be written, can be used. Then we have the next one. The speed of the sound in carbon dioxide is less than the speed of sound in air. The speed of sound in carbon dioxide is less than the speed of sound in air. All right. Use this information or otherwise describe an experiment to show refraction of sound waves. You may include diagram to your apparatus. So I have included the diagram. So this topic is generally completed with 3 when we have studied the CRO cathode ray oscilloscope as well, but since we have to complete it anyway, so I need a source of sound for it. The source of sound is a speaker, or it can be any other source of sound as well. All right, a musical instrument or anything like this. Then you need something that contains carbon dioxide. In this case, I'm using a balloon. Balloon contains CO2. And then I have the microphone, which is acting as a receiver, which would detect the sound wave once it's been refracted by the balloon. So that's there to detect the sound wave. So you just write down the source of sound, how are you going to produce the sound, what thing are you going to use, or what stuff will be used to show refraction, and how are you going to collect or receive the sound waves. This is the information that you need to write. Sound is produced using the speaker. Balloon containing CO2 is placed in between speaker and the receiving device, that is the microphone. The amplitude of the sound wave increases as it travels, since CO2 is denser than the air. So I have included the source of sound. I've included the carbon dioxide, which is contained in the balloon. Then I've included the microphone, which is going to receive the signal. You add these things, you write these things. Obviously, you won't be able to draw the speaker and the CRO itself, so you can just draw the block diagram. All right, so this is a generator that contains the speaker. All right, then you have the balloon that'll contain CO2, and then you have CRO, which is there connected to a microphone. So anything like this you have to draw. All right, moving on to the next question. So here's the next question that we have from the paper of 2022. Two parallel rays of light, one red and one blue, enter the prism, glass prism. Figure 4.1 shows both rays of light before they enter the prism. The blue ray is shown incident on the different side of the prism after passing through the prism. Okay, whatever. Let's move on to the first part. On figure 4.1, mark and label. I'm upon this one. Mark and label the angle of incidence, the angle of refraction, and angle of refraction are for the blue light as it enters the prism. Alright, so the angle of incidence would be the angle between normal. This dotted line represents normal. So angle between normal and incident would be angle of incidence. Angle between normal and the refracted ray would be angle of refraction, marked by R. Continue the path of the blue light after it strikes the left side of the prism. So after it approaches here and strikes this left side of the prism, we need to continue the path of this blue light. Now the thing is, it reads angle, the blue ray hits the left side of the prism at angle which is equal to the critical angle, and we know this thing from the theory that whenever the angle of incidence equals the critical angle, then the ray would move along the surface of the prism or surface of the object. So the ray would travel along or become parallel to the surface of the glass block. So this one is the blue ray for the blue light. Alright, because this angle equals to critical angle, it'll not be moving in this direction or any other way. It'll be perpendicular to normal or parallel to the surface. Anyway, the refractive index of the glass for red light is smaller than the refractive index for blue light. Okay, continue the path of the red light as it travels in the prism and after it strikes the left side of the prism. Now since the red light we have will be is having the refractive index for that is smaller. All right, so there would be less bending for the red light. So you can show it like this. And we also know it from the theory of electromagnetic spectrum that the red light, it bends the least, the violet or the bluish shades, they bend the most. And since this one has not reached this one has not reached the critical angle, so it'll just undergo the normal refraction, which is bend away from the normal. So over here, it'll bend away from the normal. So the final form of this one, would be something like this one. Alright, so this is a neat diagram for all of these parts, where you can see the refracted ray for the red one, the emergent ray, and the normal and stuff like that. The next thing is state what is meant by the critical angle. Alright, the definition is very important. You have to memorize the definition as it is. So for critical angle, we define it as the angle of incidence for which the angle of refraction is 90 degrees. And the ray should be moving from dense medium to less dense medium. So that'll be written as, let me just paste it over here. Alright, so here it is. Critical angle, angle of incidence for which the angle of refraction is 90, and then you can simply write when the wave moves from dense medium to less dense medium. That should be enough. Anyway, the refractive index of glass for blue light is 1.5, n equals 1.5. Refractive index is represented by n equals to 1.5. You need to find the critical angle for the blue light in glass. So C has to be found out. The formula is n equals 1 over sine C. Then you can write 1.5 equals 1 over sine C. Then sine C equals 1 over 1.5. Then you find 1 over 1.5. Whatever you get, you take sine inverse of that number, and the answer in two decimal places, in two significant figures would be 42. All right, or just you can write sine inverse of this fraction on the calculator, and you'll be getting the answer straight away. All right, moving on to the next one. Here we have another latest question. Just let me zoom it in a little bit, on hand 60. Okay, that's fine. A dentist uses a plane mirror to see the back of the tooth. The plane mirror produces an image of the object. Describe the position of the object. So the position is, first of all, on the opposite side of the mirror. All right, I'm just writing the bullets. And the second would be opposite side and same distance, and at same distance from mirror with respect to the object, or you can say the object and the image would be equidistant from the mirror. Image would be virtual, image would be upright. These are not the properties that describe the position, so you need to be very careful with it. I've seen many of the students answering this question and their answers include virtual, upright. I mean, these are not the characteristics regarding position. The position would be on the opposite side and same distance or equidistant from the mirror with respect to the object. Then we have the next one. Figure shows the plane mirror used by a dentist to see the point labeled X on the tooth. Mark the position of the image formed by the mirror. Mark the position of the image X formed by the mirror. So this is your mirror. Your image would be formed on the opposite side, and it would be, first of all, on the opposite side and equidistant from the mirror. So whatever this distance is, the distance on the other side would also be exactly the same. That's a rule. Draw a ray of light from X to show how the dentist can see the tooth. For this one, you have to follow a couple of steps. First is from the image. All right, so this is your image. You draw a line or ray from the image towards the dentist's eye, and the back side would be dotted. This side, all the rays on this side would be dotted on the back side of the mirror. And then in the next step, this is your point of incidence. You draw a ray from the object towards the point of incidence, and then the direction of arrows is away from the object. This was your object. Away from the object towards the eye. All right, so this is a rough sketch. The proper neat sketch would look something like this. All right, the image is X prime. Then you draw a ray from the image towards the eye. The back line is dotted. Then from the object towards the point of incidence, you draw a ray over there, and that's it for the image. All right, moving on to the next parts. And one of them is state one characteristic of the image formed by the plane mirror other than its position. Virtual. All right, or you can say upright. Both of them would be okay. All right, then we have the next one. The first one is refraction causes a light wave to separate into different colors. You see the least deviated is red, the most deviated is violet, and there are some other colors in between. The first part is describe the term angle of refraction. So this is the angle between. All right, I'm just writing in the short forms. You better listen to the definitions, or you can write from these short forms as well. Angle between normal and refracted ray. And refracted ray, not reflected ray, refracted ray. The angle of incidence for white light as it enters the prism is 40. The angle of refraction for the red light is 25. Calculate the angle of refractive index of the glass for red light. Show your working. So angle of incidence is same for everyone because the white light, it is composed of all the colors. So angle of incidence for the red light is also 40. The angle of refraction for the red light is 25. And you have to find the refractive index. You just use the formula sin I over sin R. All right. and refractive index of the glass. So as the ray is entering the glass, you just keep one thing in your mind. When the ray enters from less dense medium, for example air, to a dense medium, you use the formula as it is, which is this case. Because the ray is entering from air into the glass, you use the formula as it is. If it's the other way around, if the ray enters from dense medium to less dense medium, you just reverse the formula. So that'll be sine r over sine I. Alright, and the rule of thumb is whatever the bigger angle is, that should be in the numerator. So sine I, sine of 40 divided by sine of 25. The bigger angle always in the numerator. Stay and explain how the refractive index for the red light differs from the refractive index for the violet light. So red light has higher wavelength and less frequency. Alright, and the more the frequency or the more the wavelength, the more the wavelength, the more the less the bending. Blue light, a violet light, it has low wavelength and higher frequency. And the higher the frequency, the higher the bending. So the red light would travel faster, the blue light would travel slower. It'll be slowed down more compared to the red light. In air, all of those colors have the same speed, but their speed is different in the medium. That's why they are separated. Alright, so name the invisible radiation found at P and invisible radiation found at Q. So the mnemonic is rugby match is very unlike xylophone game. So we are having visible light, so here we'll be having infrared, and here we'll be having ultraviolet, or UV IR over there and UV over here. UV light has more frequency, infrared waves have less frequency than the visible light. Alright, moving on to the next one. Ultrasound and X-rays are both used in medical imaging. Define what is meant by ultrasound. Alright, so for theory question, I'll be opening the solved one. Yeah, so yeah, here we have in the middle. Define what is meant by ultrasound. So sound with frequency above 20,000 hertz, which cannot be detected by the human ears, these are called ultrasound. Alright, so ultrasound are the sound waves with the frequency above the audible frequency for humans. Describe what happens to the ultrasound as they meet the boundary between two different materials. Some of the ultrasound or some of the sound waves, or ultrasound in this case, would be reflected, and some of the ultrasound waves would be absorbed by the material. Because of their energy, some of them would be absorbed and some of the ultrasound would be reflected. Alright, then we have this one. So they send a pulse which is represented as a signal A, then it goes to the receiver and it is received once again. The pulse is received after a time of 0.05 millisecond, which is stated or marked as interval B. The average speed of the ultrasound in the human tissue is 1500. Calculate the distance between emitter and the child. Alright, so first of all, you write down the formula for distance. Distance equals speed into time. Speed into time. Speed is given 1500. There is no issue with the speed. The entire issue or the entire question is regarding the time. So you need to calculate the time first. Just let me raise it off. Now the thing is the time for the two-way trip. All right, the time from the emitter to the receiver and back to the emitter, the time for the two-way trip is the difference of 0.02 and 0.05. This is the time for the two-way trip, which is 0.05, because in the middle of 0.04 and 0.06 you must be having 0.05. So 0.05 minus 0.02, so they'll leave you with 0.03. This is 0.303 is the milliseconds is the time for the two-way trip. What would be the time for the one-way trip between A and B, between the emitter and the collector? That'll be half of it. So half of 0.03 would be 0.03 divided by 2, which would be 0.015. All right, so it'll be 0.015 millisecond. This is the time, but you need to get rid of the millisecond as well, so you can divide. So the thing is, we can get rid of the millisecond and we can go to the standard unit, which is second, by dividing by 1000. So you divide by 1000, and then the final answer after plugging each and everything in the formula would be 0.022 meters into significant figures. Moving on to the next one, the speed of the ultrasound in human tissue is close to the speed of sound in water. Suggest the approximate values. Speed of sound in gases is anything between 300 and 350 meter per second. Anything in between. Speed of sound in solids is anything between 2000 to 6000 or even to 10,000 meter per second, because it depends on the type of solid as well. Alright, describe what happens to the X-rays to produce this image. This image of the bones of the hand is being produced by the X-rays. How do we use the X-rays to produce this image? So the bottom line is the X-rays are able to pass through the flesh, but the X-rays are absorbed and blocked by the bones. So the part of the image that is white in color, this one, this is a portion where the X-rays were blocked by the bones and they were unable to reach the detector. The part of the image that is dark, like this one, representing the flesh, this is a portion where X-rays were able to penetrate through the hand and were received by the detector. So this is a final verdict. X-rays are passed through the tissues, the soft tissues or the flesh, and they reach the detector. Hence that portion is dark, because we have a signal. The dark represents, yes, we have received the X-rays. X-rays are absorbed by the bones, blocked by the bones, and they do not reach the detector. Hence that portion is light, or the lighter it is, it means we did not receive the X-ray signal from there. Wavelength for the X-ray is given that many meters. The electromagnetic speed is given that many meter per second. You need to calculate its frequency. We have the standard formula V equals to F times lambda. You can rearrange for frequency, hit it on the calculator. Make sure when you're hitting on the calculator, you always press the fraction symbol first, because otherwise calculator use the mass rule and your answer might be incorrect. All right, then we have the next one. Figure 8.1 shows the ripple tank and the crust of the water waves that is produced in it. The frequency of the water wave is 2 hertz, all right, means 2 waves per second, and its amplitude is 3 millimeters. All right, amplitude means the maximum displacement from the mean position. Calculate the number of crusts produced in 1.5 seconds. All right, so 2 hertz mean 2 waves in 1 second. All right, in 1 second we have 2 waves. How many waves would be there in 1.5 seconds? We can do it by cross multiplication. Then you hit it on the calculator. There'll be 3 waves in 1.5 seconds. On the graph, draw a graph to show how the height of the wave at the point varies with time. So we need 2 pieces of information. One is about the frequency, and the second is about the what do we call the amplitude. So first of all, we can draw a mean position at 0. A red line, or the represented by a red line, this is a mean position drawn at 0. The maximum displacement from this mean position has to be 3 because the amplitude is 3 millimeters. All right, so the maximum that the wave has to go up or down has to be 3. So you can draw a mark over here, mark over here, mark over here. It has to go a maximum of what do you call that, 3. Then the next thing is, what should be the length, or what should be the length of the wave? In this case, the length of the wave is representing time. The horizontal distance of the wave is representing time. So we have the frequency as 2 hertz. 2 hertz means in 1 second there has to be 2 waves. So this is a mark from 1 second. So from the starting position till this mark, there has to be exactly 2 waves. And the maximum height of those 2 waves has to be 3 millimeters. So the only way that you draw a wave which satisfy both these conditions is this one. You see, in 1 second we have 2 waves, in half a second we have 1 wave, and the height of the wave, the maximum height of the wave is 3 millimeters. Moving on to the next one. The frequency of the wave is increased. Describe how the apparatus in 8.1 is adjusted so the frequency of the wave is increased. The waves are being produced by moving the rubber band, by moving the wooden bar attached with the rubber band up and down. If you move it faster, the frequency of the waves would be increased, because in that case you'll be producing more waves per second. See what happens to the speed and wavelength of the wave as the frequency increases. Speed does not change, speed remains same, and the wavelength would decrease. Alright, because the speed of the waves, you have increased the frequency. Alright, you have increased the frequency, and the speed will remain same, and the speed will remain same only if the wavelength has now been decreased, because once you increase the frequency, the wavelength automatically decreases. And the product of these two, which is V equals to F times lambda, if one thing is being increased, the other thing is being decreased, the product would be same. So it would appear that there's no change in the speed. The apparatus shown in figure 8.1 can be used to demonstrate refraction. State the additional apparatus used to demonstrate refraction. Glass block or a wooden block. And what do? You place a wooden block somewhere over here. What happens with the wooden block or the glass block? The depth of the water changes. And refraction for the water waves occurs due to change in the depth. So all you need to do is place the wooden block, place the glass block in the ripple tank, and the portion where you place the glass block, the depth of the water would be decreased because some of the portion has been occupied by the glass block. So that would be the region of shallow water. And once you have 2 different regions, 2 different depths, refraction occurs. Draw on figure 8.1 to show the refraction. Now the thing is, you're entering from deep water to shallow water. How do we know shallow water? Because after the barrier, this is a portion where you place the barrier. This is a shallow water now, because some of the portion in the ripple tank is occupied by the barrier itself. As the waves enter from deep water to shallow water, their wavelength decreases, and that's why you'll need to bend the waves backward. So first, these are the incident wave fronts. Then you have a barrier over here. After the barrier, the waves bend backward because the wavelength has to be decreased. So you have high wavelength here, less wavelength over here. If you bend the waves, let's say in this direction, that would mean you have small wavelength over here, and in shallow water you have high wavelength, which should not be the case. In shallow water, the wavelength should always be less. All right, moving on to the next one. $175, yeah. A collector views a postage stamp of height 1.5 centimeter through the lens. The lens is 2 centimeter from the stamp. Linear magnification of 3. Okay, means the image is 3 times bigger than the object. This is a full scale. Okay, a ray of light from the top of the stamp to the lens is shown on figure 3.1. State the type of the lens used. We have the convex lens over here, which is used to produce the image of the stamp. State what is meant by the linear magnification. Ratio of height of the image to the height of object. This is how we define linear magnification. Complete path of the ray from top of the stamp after it passes through the lens. This one I have represented with the blue one. All right, so all I did was I joined the top of the image to the top of the stamp, and the ray was passing to the center of the lens. Any ray that passes to the center of lens goes undeviated. This is one of the property that we study in theory. So that was it for that part. Use your drawing to determine the focal length of the lens. All right, so focal length, I drew another ray, all right, which was this one over here. This ray, previously it was parallel to the principal axis. After refraction, it has to go from the principal focus. Now I should bend this ray in such a way that if I extend it backward, it should pass through the top of the object, because only then you can have a point of intersection. So this ray was extended backward, and the point that it passes or it touches the principal axis is the focal length. Then you measure the small number of blocks. I had 15 blocks there. 5 blocks represent 1 centimeter, then 15 blocks would represent 3 centimeter. Sorry, 5 centimeter. Oh, sorry, 3 centimeter. Yeah. So from the center, I had 15 blocks. Each 5 blocks represent 1 centimeter. So 15 blocks, they'll represent 3 centimeter. Okay. Draw 2 additional rays from the top of the stamp to show how the image is formed. So I've drawn 2 rays. One of them is the red one, and there's another one, green. This point is also focal length. How do we know? 15 blocks from the right, 15 blocks from the left, both would be f. 15 blocks further to the right would be 2f. 15 blocks further to the left would be 2f on both sides. Then if a ray is approaching the lens after coming from the principal axis, it becomes parallel to the principal axis. This is the third property that we study. So I drew all 3 rays for this one. All right, then we have the next one. The 3 angles of a glass prism are 45, 45, 90. Light travels more slowly in glass than in air. State what happens to the wavelength of the light in the ray as it enters the glass. Wavelength decreases. So does the speed. What happens to the frequency of the light as it enters the glass? The frequency remains same. All right, these are the properties, these are the facts, pointers that we study in theory. Calculate the refractive index. Sorry, the refractive index is given 1.6. You need to calculate the critical angle. Once again, the same question, we did it already. The formula is n equals sine 1 over sine c. You can make sine c the subject, then you can find the sine inverse. That'll give you the value of c, which in two significant figures is 39. Sketch the path of light as it strikes the side of the prism at z and after it returns to the air. And the one of the information. So the critical angle is 39. We have to keep it in our mind. As this ray enters over here, which is entering perpendicularly, and at this point, if these two angles are 45, then that angle of incidence would also be 45. So I had written it down over here. This angle is 45. The critical angle was 39. Critical angle was 39. Angle of incidence is even greater than the critical angle. So what happens? Total internal reflection. The ray was reflected at the same angle of 45, and once it approaches over here, you see it is hitting the surface perpendicularly. And if the ray of light hits the surface perpendicularly, it goes undeviated. So it goes undeviated once again. And we're done with this one as well.